that means is that from initial concept to a built building, we work with clients through all those phases. So there's the programming schematic phase where we sit down and talk about what the goals are, what the project's about, and then we work through with a series of renderings and drawings, putting that together, and then we work with contractors through the construction phase to get that built. And so the project architect is kind of the guy that's with the client from the beginning to the end, and knows the real nuts and bolts of the project. That's where I'm at. And what we were asked to talk about something obviously STEM related, but also what got us involved in architecture. And a big part of that for me was environmental home design. Buildings account for quite a bit of greenhouse gas. A lot of people think of cars, things like that, but buildings actually are much more significant contributor to greenhouse gases. And I think it's in the next 20 years, 3/4 of buildings will be new or renovated. So we're kind of at this point where there's a huge opportunity. If we design things properly, we can cut the emissions pretty substantially. And the goal is by 2030 to have carbon neutral buildings, which is kind of lofty, especially where we are now. And as you guess, there's a lot of things that go into this. There's thermal design, there's the materials you use, recycled content. One of the really big factors is solar design. So what I was going to do is take you through today the 3 fundamental ways we analyze buildings based on the sun. This has to do with the openings you punch in the wall, how you shade it, how you orient the building on the site. And so there's 3 ways we can analyze that. I'm going to start with the most fundamental, and I'll get you through this quickly because it's the technical. It's kind of like taking your vegetables, learning how to do this stuff. This is something I haven't done since college. But it's worth understanding, and it's kind of interesting. So this is a sun chart, and there's one of these for every latitude on Earth. I picked 40 degrees north latitude, which is pretty close to where St. Louis is. And these Roman numerals on the side here represent the months, and then the numbers going across the top represent the time of day. So theoretically, you can find the intersection of any month and time. The months are on the 21st, so there's a little bit of leeway, but you can find the intersection of any day of the year and any time of day and find out where the sun is in the sky and how it's going to cast shadows. And if you go ahead and open up that 11 by 17, that's kind of laid out as an exercise, but I'm not going to put you through that. We're going to waste all our time on it, so I'll just real quick walk you through it. So basically what I've drawn on there, if you look at the top, there's the plan of a wall with a window cut into it. So wall, window cut into it, and then down here there's a section that shows the height of the wall and the height of the window. And I think I've called out to look for August 21st at 10 a.m. So if we go back to our solar chart, I've highlighted those lines. Find August 21st, follow down the line, 10 a.m. And then if you follow from the center of the circle out, you can get your degree of where the sun is, at what angle the sun is hitting your building. And if you follow the concentric circles around, the red line, you can find what angle parallel to the ground it's hitting your building. So how high the sun is in the sky, essentially. And so with basic geometry, you've got 54 degrees off south is the angle that it's hitting your building. And I think it's about 51 or so degrees off the ground it's hitting your building. So if you go back to that little diagram that's set up there, you can see I've drawn a 54-degree angle hitting that window and hitting the edge of every wall, which shows the angle of the shadow. And then likewise, I've got the 50-degree altitude, which is the height of the sun, and how far that projects the shadow. And then if you line that up, you can basically get how the shadows are going to react on your building for different times of day. And obviously, as you guessed, this is just a wall with a window in it, and there's several steps involved. For doing a whole building, this takes hours and days to cast all, but it's kind of like doing a coloring book. You just kind of zone out and you just start drafting lines. And it's kind of fun because you can calculate this just using a compass and a protractor, and basically with geometry draft the lines, but you could also use geometry. You've got heights and lengths, and then you can find the angles using trig, essentially, sine, cosine, tangent. So that's kind of the meat and potatoes. That's how they did before computers. You're out there drafting and finding the effects on the shadows. And it's really important to find that angle because, as you already know, I'm sure, in the summer, the sun's much higher, it's much hotter. In the winter, it's much lower. You probably want some of that light in your building because it warms the space. So how we design our window openings has a big effect. And you'll find that on historic buildings even, things that we take for granted, were actually designed a lot because of solar and the climate. So you could probably guess this is in the South, it's in New Orleans. Big porches, we associate this kind of architecture with the climate it comes from. Likewise, these neoclassical buildings also from the South, where it's really important to shade from the sun. More modern buildings, it looks quite a bit different, but it's doing the same thing. They're horizontal louvers, and in using that basic exercise we just did, we can find out how wide the louvers should be, how they should be spaced, and what times of year different parts of the building should be shaded. And then we use that to design the HVAC systems and the energy load on the building, essentially. All right, they're getting here just the right time after I've gotten through that algebra and trig stuff. So, as I said, that's how we did it before computers. Thankfully, we don't have to go through that each time we analyze buildings now. So this is, I think I heard somebody mention they're from the Lindbergh School District. Is that in this group? So this is the new Lindbergh Administrative Center that's being built. And we basically build every bit and part of the building. Structure, mechanical systems, windows. And you're looking at the end of the design phase. But as we work through this, these things are just masked up, kind of like clay models. But what you can see is I can basically pick the exact spot geographically where this building is and overlay the compass and then analyze how the sun moves. And I'll take you inside the building in a second, but just so you get an idea of how that works. I basically set the exact address, I picked the time of year, and then I've picked a range. So I'm doing a full day on January 21st, day in the winter. So you can see, it shows you how the sun moves across the sky on the building. And then what gets really interesting is you can go in, this is really rough and it's kind of technical, but you can do the same thing inside the building and see how that sun moves across the space. Now this is the winter, you can see the sun blasting into the space there. Set one up for the summer and you almost see no sun at all. So you're still getting indirect light. The space is being lit by the south, but you've blocked that harsh south light. Hi, welcome. I was just mentioning this is Lindbergh's administrative offices, and we're talking about how we use modeling and different systems to calculate how the sun affects the building systems, causing different energy loads and human comfort. So you can see across the south face of the building, we have all these louvers going across the front like little shells, and we basically use that system that I just showed you to design how frequently they should be spaced and how deep they should be. And you can get real technical. We don't do this on every project, but we certainly could, where you can actually find the foot candles of how much light is hitting each space. Because you need obviously a certain number of foot candles on your desk floor. So we really can tweak the louvers and the openings to provide indirect light. So that's not only warming your building in the winter and cooling it in the summer, but it's also reducing the amount of lights you need to have running.
Are you guys doing stuff with Dressel too? And we walked by and saw some pictures. So.
Yeah, and that's similar. You'll notice Dressel has a lot of windows on it. It's a lot of curtain wall, so it's really important to pay attention to that. Now I'm kind of blocked. There's a lot more that goes into this. For example, the glazing type in and of itself. There's coatings that do reflective things. So it can get pretty involved, but fundamentally, yeah, similar thing. That's how we do that. And then as we bring it in, this is more of a technical model. As we bring it into further along the design process, we start to render those things out a little more, how you're seeing that image. But we actually put finishes and materials on that space, and those affect how the light reflects or absorbs more. And then you can see how that light will move across the bay with the actual finishes and how that affects it. So that's understanding fundamentally how that sun chart works that I had showed you before is the starting point of understanding how you start to lay out the building, and then as you get more technical into it, you can fine tune the building how you want. And then probably, this isn't something, similarly, this is something I did a lot more in college than in the real world, but this is also the most fun way to do it. This is actually this piece of that model, of that digital model here. So I've basically taken this corner here and modeled it up to scale. And you can find, similar to the sun chart, there's something called a sun peg chart. And this is for 40 degrees north latitude. And it basically tells you to cut a peg a certain height, stick it in the center there, and I'll have to do this. You're not all going to be able to see this at once, and I'm going to try not to blind you. But if you take the tip of the shadow of the peg and point it at that intersection, August 21st at 10 a.m., if you look, you can see in the model there, you can see how those shadows move across the bay. And so likewise, if you go up to January at 10 a.m., you can see how the light's getting into that space. And so these are really fun. I didn't want to take you guys out in the triple digit heat. These are great to use outside because obviously so August at 10 a.m. is right there. You take that out.
So using that chart, it tells you kind of where to hold your light source.
So I'm actually moving the light source to tell me what time of year I want to see the shadows in the model. So this is an open office workspace in here. And if I want to see how bad those employees are going to get blasted, for example, on January in the morning, if I make the tip of that shadow of that peg hit that intersection of that time of day, it'll have the same effect of what the sun would do at that time of year. So like I said, these are outside, they're much more accurate because the light up close kind of blurs the shadows. But you can have a lot of fun playing around with those, and I think I include these on here pretty stoutly, but usually you can take these pieces off and use different scraps to just kind of work with it and see how that affects how that's going to light your building. And that's something cool. So. Yeah, that's really fun because it's something you can just go on and keep your hands dirty and just see how it affects it. And there's actually, I didn't do it here, but if you really want to get more involved, you can. I basically cut this into cross section so you could see into it because it's a group. But you can actually close the building off completely. And if you use like a peephole you have in your front door at home and put it in there, you look kind of like a nerd doing it, but you can kind of look into the box and it gives you the feel that you're in the space, kind of oddly with fish eyes, which is really fun to do. So taking you through that, I just want to show you some more images of how you might see these around town. A lot of times you see these elements on buildings and they look decorative. Sometimes they are. People put them on buildings just to kind of make the facade look interesting. But there's a lot of unique ways that when you look at buildings, a lot of it is done to control the sun. For example, outboard systems, and this one's actually supporting photovoltaics, which makes a lot of sense because you're providing shade and you're getting the power. You're getting that double payback. This project's in the Loop, and it's actually LEED Platinum. I don't know if you guys have heard the term LEED before. It's Leadership in Energy and Environmental Design. They're kind of a subset, they're a group within architecture that has been pushing hard to make buildings more environmentally sensitive, and it's kind of a rating system. But a big way that they achieved that was getting southern light while also protecting the building from extreme heat glare. So that's at night. So that's just up on Delmar. Similarly, on a lot of buildings, especially schools, you'll see light shelves, and these do something interesting in that they're kind of midway in the window. So what it does is it shades the space where people are actually working, so it blocks your computer screen from getting glare. But on the inside of the building, on the top side, it bounces that indirect light further back. So this is a pretty effective way, like I said, we do that on a lot of buildings, to get light back into the space. One thing I don't think I touched on, but you can see it on the model there, south facing because of the sunworks, how we saw on the solar chart. When you see louvers that are horizontally oriented, you're generally looking at the south face of the building. The sun is high, it's usually facing that building pretty directly. East and west side, you generally see vertical louvers because the sun is much sharper in the sky and it's coming in your building at odd angles. It's much more difficult to control.
So is this like what a lot of the architecture is going to start to look like with most modern
Hopefully.
buildings? It's like a lot of the louvers going,
Right.
so it'll be a very similar look to this.
Right, and that brings me to another point I want to make. Buildings that are efficient and don't use a lot of energy often look like they are. When you just see boxes with glass, generally they haven't considered any of this. Buildings should look like where they come from, which brings me back to those initial slides I showed you, where when you look at a building from New Orleans, it looks like a building from New Orleans. That's because they built that because it fits that climate. Which hopefully we're going to start, in the 80s, 70s and 80s, that all kind of went away as oil and energy took off and people started to forget about needing to do that kind of thing. But hopefully, like you said, we start to return to that. So one of those vertical louvers.
I think it's like where you're at within the country too. You
Absolutely.
see more of different, because like a lot of these reminds me of the casinos in Las Vegas. Like before, they were just one big sheet of glass.
Right.
And now that they're tearing them down or building, a lot of the condos and, high rises and
Right.
stuff are looking like this.
And it's starting to just make more business sense too. You run a more efficient building.
Right.
To keep on the rent you charge, And so likewise, there's any number of things. This planting, it's called a green screen. Plantings work great because in the summer, when everything's in bloom, it shades your building. But in the winter, that dies off, and then you get the winter light in your building more.
Where is that?
This, I think it's in Japan. And likewise, in Milwaukee, there's actually, I've been talking about passive design, so things that are most efficient, but they never move. It's just a static system. This is the Art Museum edition in Milwaukee, and it actually moves. So those cantilever wings you see respond to the sun and move up and down to shade or not shade. So those are awesome. They're also very pricey and maintenance heavy, as you would guess, but they definitely get the job done or required. And likewise, this is in Paris. It's the Arab Institute. Each one of these windows is a mechanical iris that, when hit with the sun, will either open or close, depending on how it works. And obviously, it's the Arab Institute, so it's making reference to Islamic art and has that repetition. But they also integrated in the environmental factor to make that work. So you can see some of them are closed, some of them are open. I've heard from people who have been there about 60% of them work. The rest of them have been frozen where they got they last left off. But this was done, I think, 20 or 30 years ago. It's been around for a while. So just another example of the system. As we get into 3D printing, the sky is really the limit on what you can do to screen those walls and how that works. So we've been talking about how to get light into the building and the walls, and that's what I've shown you there. The roof is another great spot. And making reference to old ways of doing things, sawtooth roofs. If you look around industrial areas, you'll see a lot of buildings sawtooth roofs because they're big facilities that don't have a lot of exterior walls, so they get lighted from the rooftop. It saves a lot of money on lighting and energy, and creates really well-lit spaces. So as I was saying, you see this really modern building. It looks like they're just doing something wacky, but they're actually referencing something that's been a long-standing tradition for lighting buildings. And this is actually Rockwood Eureka High School, a project we just did. If you go out there now, this was early in the design phase. We weren't able to carry this through, but early on, we were exploring having to weight room unit with sawtooth force to get natural light in there. And I'm almost wrapping up here. This is an art museum in Texas, and it looks like a bunch of barrel vaults with these little monitors on the roof, bringing natural and direct light through the roof that way. See, the light comes in, bounces around, and comes out. And lastly, and one of my favorite products in architecture is called Solitude, and you may have heard of it or maybe seen it in some of your schools. Interior spaces that are hard to light. This is basically ductwork for sunlight. You can run it pretty far, 50, 60 feet, and it basically shoots a laser beam of sunlight into your space. And there's a lot of different ways to use it. This is a project in Colorado at an elementary school to get natural light in to save those energy costs. And I've been talking a lot about the environmental, but even human health factors. They found that companies, for example, that have natural light report significantly less sick days, more productivity. I've heard, you would know better, but supposedly it makes children less rowdy and more calm, less anxious. Yeah, exactly, right. And so that concludes the solar design presentation.
Awesome.
Yeah.